Ladies and gentlemen, welcome to the ICE technical meeting, Offshore Fixed Platform Construction. This event is brought to you by the Institution of Civil Engineers, ICE. My name is Daniel. I am from ICE Student Chapter, BINUS University, and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this evening. First, I will be reading the rules of the webinar. After that, the event will be guided by the chairman of ICE-JLA Local Association, Phil Woodmansey, as our moderator to start the presentation of our featured speaker, Abimanyu Satrio Ambiarto, and later will be followed by the main speaker, Achmad Makmur. The event will then continue with a Q&A session. Now, ladies and gentlemen, for your own convenience, please pay attention to the following rules. First, for online attendees, you can ask your question to the speaker by pressing the raise hand feature located at the bottom of the screen. For those who attend on-site at Kemang, you can later raise your hand and the moderator will let you ask the question. The question should be in English. Second, you can raise your question after the presentation of the speaker. Now, I would like to invite the chairman of ICE-JLA Local Association, Phil Woodmansey, to give his opening remarks and also guide this webinar onwards. To Phil Woodmansey, the time is yours.
Okay, before Phil takes the floor, which he will do in a minute, I would just like to spend a few seconds introducing the event tonight in general. And first of all, just to welcome you to this first IC technical meeting of 2023. My name is Mike Doby. Because I wasn't introduced, I'll mention it to you. First of all, I would welcome all of those who are attending online. We have a growing number here at the event. I would like to say that we have the aim to have more and more people coming to the events and less people online. But the nice thing about having the online side of the event is, of course, we can have quite a few people listening in from outside Indonesia, which is a target that we have now and we would like to continue to do. So that's how we want to move forward. As usual, we will be aiming to hold these events approximately once per month, maybe not every single month, but most months of this year. And we certainly have some interesting ones already planned, and we will try to get notices out to everybody as early as we can for each of these events. I'm not going to say too much about tonight. The details of that will come from Phil, but it's a rather special occasion because we have two speakers. This is something we've done in the past, and we think it would be very good to continue this, and that is to have a short presentation from a student member who will tell us something about the work they've been doing as part of their studying and their course at university. That presentation will be a little bit shorter, about 15 minutes or so, which is quite difficult to make a presentation in 15 minutes. So we'll see how Abim gets on in a minute with that. And then that'll be followed by our full presentation from Achmad Makmur, which is all about offshore platforms and hearing about some of his experience in that field. But the more detail about that in a minute. But again, for me, thank you all for attending, especially here in the Eastern Promise. I said we have a slightly growing number. We're expecting a few more to arrive before too long, we hope. And I will hand over now to Phil and ask Phil to lead you through the event this evening. Thanks, Phil.
Yep, thanks, Mike. And once again, thanks to Reef and the team for setting everything up tonight. Tonight's quite a topical subject. We've all seen the horrendous devastation in Turkey and Syria following the massive earthquake there. And it really shows what can happen when civil engineers don't pay close attention to construction supervision. Making sure things are built properly, making sure there's good quality, and making sure they're safe. There's been about over 40,000 people killed over there, probably up to $50 billion worth of damage, and around 20 million people displaced from their homes. So when civil engineers don't do their job, it really can be a very serious problem. So tonight's a good topic. It's about improving construction supervision. The first speaker, would like to welcome Abim. Abim is actually a past president of the student chapter of ICE. So, and he's a little bit of a star, actually. He's been most outstanding student in 2021. He's been a lab intern, quantity surveyor. He's been a lab manager and a research assistant. And so we're really glad that Abim has come back to talk to us, and very welcome, Abim. So I'll let you get on very quickly. And of course, welcome to our main speaker, Achmad. Achmad is a offshore and marine engineer, civil and structural. He currently works for BP, but I learned tonight that he's actually changing company soon. But anyway, I'm glad that we've caught him before he moves, and he'll be talking to about construction supervision and quality on offshore platforms. So I think that's enough. Let's get on with the main event, and Abim, please, over to you.
Okay, that's I think the mic. Thank you for the warm regards, Phil. I'm gonna go ahead and share my presentation right here. Okay. If the Zoom can see it clearly, please let me know, and I'm gonna start my presentation. So, good evening, everybody. My name is Abimanyu, or also known as Abim, and in this wonderful night, I'm going to try to mashed up all my research thesis into a 20-minute or 15 minutes presentation. So wish me luck on that. But yeah, so it's about project supervision. So it's about project supervision. And my study is about the optimization, study integrating photogrammetry and 3D laser scanning in BIM for construction project monitoring. And to conduct this research, I use a case study on the Trans-Sumatera Toll Road on its Binjai to Brandan segment. So before I get started, I want to explain the discussion outline. I would go, it's like a thesis. So I would go step by step from its background to analysis and conclusion. And I want to go ahead and discuss a bit about project monitoring. So what is project monitoring, right? The main issue that I raised to answer this thesis problem is the lack of technology adaptation or digitization in construction project monitoring is the main issue. So about the project monitoring itself, it's actually an activity that are held with the aim to ensure that things should go as they should, right? And then how can we achieve this effective project monitoring? And I derive this into a 3 bullet points. The first one is to have a very good project management communication skills. To do so, we need to be able to compare the plan and real condition study, and as well as integrating the 3 constraints of project management, which are the quality, time, and cost itself. Now, what are the current conditions, especially in Indonesia itself? I conducted a study with Utama Karya, where the study showed that traditional monitoring relatively uses a large capital outlays and involves a complex list of activities, where this leads to a time-consuming progress tracking. So that's one. The second reason being an inaccurate results because the large amount of human error factors. And the third result being the scattered data if the project is in a large scale, for example, highways, dams, like it is used in this research. So let's move on to several state-of-the-art. I did some preliminary research, and I found this for articles from 2015 to 2020. I think this is pretty holistic, yeah. And what I found from these 4 articles is that photogrammetry and 3D laser scanning are the 2 cutting-edge inventions or technology that are being adapted in civil engineering works. And I highlighted 2 of the 4, where this will be compared to my study later on in the analysis sector. So the first one is about photogrammetry, and the second one is about 3D laser scanning. And let's go ahead and focus on this research more. I have two main problem formulation in this research. The first one is how can I improve the optimization itself? And then what is deviation value? Deviation value means that is the quality of this digitized monitoring method is suitable enough to replace the conventional method. So that is what I want to find out in this research. And thus the two main focuses in the research. The first one is to analyze the main parameters that are being affected, to analyze the second objective, to obtain the most effective monitoring method. So those are the two objectives. And I have also two hypotheses in this research. The first one is that I think my research can be used as a remote project supervision. And the second one is that the 3D laser scanning data will propose a better accuracy compared to the photogrammetry method. Okay, so that's for my background. I think before we go ahead and go to the research methodology and other analysis, I want to lay a couple of details on photogrammetry itself and 3D laser scanning, so we all start off in the with the same background. So for photogrammetry, it is essentially basically a technique used to measure the position, shape, and size of objects in the real world using a collection of pictures or images. Now, the most common misconception about photogrammetry is that these pictures need to being collected by using an aerial device. But in reality, we can use our phones or a DSLR camera to achieve that. The main distinction of a photogrammetry is that the pictures, the images, have data, geolocation data, time data, and other data. But for this research, I do use an aerial photography method using the DJI Phantom 4 RTK. And the next one being the 3D laser scanning. It is actually quite fun doing this research because, well, we'll see in a later analysis, but it is a very expensive tool. It's a very high investment tool, and it is revolutionizing the ability to characterize surface properties and can generate high quality data at previously unattainable scales and resolutions. Now, there are actually two methods in using the 3D laser scanning. The first one is using the time of flight method, and the second one is using the phase-based method. But I don't want to bore you with all the details. This research is going to use the phase-based method because we are going to use the terrestrial laser scanner tool based on our case study, because it is a highway and it is only a 200-meter study. We don't need a mobile laser scanner to achieve all that monitoring process. Now, let's move on to the research methodology itself. Well, I have my research flow over there, but what I want to focus more is about this table. I have conducted a primary research and secondary research, and I have also classified this research to achieve several results that I want to get. So in this instance, I want to focus on the data acquisition part. There are photogrammetry and 3D laser scanning right there, and there are point cloud data. So we are going to talk a lot about point cloud data later on, because point cloud is essentially the data that we gather from doing the photogrammetry and 3D laser scanning. So those two have point cloud data in common. So that is what we are going to compare. And this study I also used 5 applications, 5 softwares, including this software. And let's move on to the research analysis itself. I'm not gonna discuss it too long. I'm going to divide it into 3 parts. The first one is acquiring the data. The second one is processing the data, and then we are going to discuss the data, the results. So in this case study, I selected the Binjai Brandan segment of the Trans-Sumatra Toll Road from STA 28700 to STA 28900, only 200 meters, where in this case, its width is only 20 to 25 meters. Yeah. So the reason being is that this research only measures the reliability and validity of each monitoring method. That is why we only selected this short of a case study. And then moving on to the acquiring data section, I will also divide the section into 3 parts: acquiring data into the conventional method, photography method, and also the 3D laser scanning method. So in its conventional method, we use the total station tool. It's pretty basic, but what we got is that we received this table of coordinates with a 25 meters interval, with the aim as a benchmark So the conventional method is here only as a benchmark, only as a control value for the other two digitized methods to compare on. So these are the results, and then let's move on to photogrammetry. It's actually quite complex compared to previous step. The photogrammetry requires a GCP or ground control points. It is basically just a marking on the ground. So when we do the data processing later on, we can see these markings, and these markings have their own coordinates, as can be observed in the table right there. But we use these markings, we use these coordinates to compare the coordinate in the data in the picture with the real life coordinate. So this ultimately increases the accuracy of later data processing. It's only for that. And then there are also several other steps, including the preparing the flight plan itself, like the vertical overlap, horizontal overlap, and other stuff, and also the flight execution. Now, from this data, acquiring data, we received the results of a 294 images, where every single of these images have its geolocation data. And we used about 32 minutes and 12 seconds of acquiring this data. So these two results are going to be compared later on with the other monitoring methods. Okay, now let's move on to the 3D laser scanning data acquisition. The first step is actually quite similar. We want to also decide which coordinates that we are going to use, which measurement points that we are going to use. In this case, for a 200-meter length and 20-meter wide area, we use 5 measurement points. And on those 5 measurement points, we also place a small checkerboard figure like so. The function of this figure is pretty similar to the GCP like before, where in later data processing, we can kind of overlay the checkerboards on top of each other. So when the data of measurement point 1 to 2 to 3, we can overlay it by using the checkerboards. So it's all in place, like so. And then the results is that because we use 5 measurement points, we also receive 5 separate raw point cloud measurement points, raw point cloud data. Okay, so that's for data acquisition. Let's move on to data processing. Bear with me. So in this data processing, again, the function of conventional method data processing is only solely for a benchmark to be compared on the other 2 digitized methods. Is it reliable? Is it valid? Like so. So from the table of coordinates that I received, I mapped a figure like so to compare the volume later on. And then for photogrammetry, it's again quite complicated compared to previous method. We need to extract data itself because from photogrammetry, the data that we got is 294 images. And then from those images, we need to convert to a point cloud data. We need to extract the data. So in doing so, I use the Pix4D mapper as the software to densify and auto-rectificate the data to create a point cloud file. Once the point cloud data is obtained and then all the work quality checking is all good, we can go ahead and go to the next step to filter this data because there are a lot of data pollution here. Data pollution, is like trees, cars, people, trucks, and everything that has nothing to do with the groundwork, with the data that I'm working on. So we need to do that to separate those data manually. Well, in future research, I was hoping that there are some sort of technology that can identify these properties, so they can automatically analyze each variables. But yeah, I did it manually to remove all the pollution of the data. And then the third step is to create the surface model. Again, the function of data processing is to compare it with the conventional method. So I need to be able to construct the surface model for 2 reasons. The first one is to visualize the work progress that, for example, if I was a manager or a contractor, I can say to my client, "Oh, this is your work progress." I can visualize it clearly. And the second reason being is to compare the volume quantification, to be overlaid and compare with the coordinate mapping from conventional method. So those are the 2 reasons. And let's go ahead to the last data processing, the 3D laser scanning. As I said before, we have 5 measurement points of point cloud data. So we have to stitch all those data into a 1 point cloud data. To do so, I use the Leica Cyclone software, and then we do it one at a time to align those data one at a time. And then we get something like this. Now, The second and third step is actually the same as before. We need to filter the point cloud data of all the pollutions that are happening. And also we need to generate the surface model to be able to compare it with the conventional method. Now, all the data processing is done. It's time to discuss the results. It's actually quite, it's a lot to analyze. There are a couple of tables here, but I deliberately divided these tables into three main categories. The first one is quality, time, and cost, of course. Now, in terms of observing equality, I analyzed its area and its volume quantification per 25 meters. In doing so, I am able to compare each volume results from conventional method, from photogrammetry, and also 3D laser scanning, thus comparing it and its deviation value. And result, I received about 2.87% deviation value for photogrammetry and 3.278% for 3D laser scanning. And then for its time, I divided into two parts. The first one is the data acquisition part, and the second one is the time required to process the data. Now, the third aspect is about the cost. I compared two main categories. The first one is the fixed cost, and the second one is operational cost. The fixed cost includes all the tools, and the operational cost includes like the accommodation, the fuel, and everything that is involved. Now, I think I can merge all this table into one table, one single table that we can easily understand. But bear with me, it is in Indonesia because I forgot to translate it. It's from my thesis. But let's look at this table row by row. The first row is about the volume. Now, as we can see here, the volume of photogrammetry is actually lesser than 3D laser scanning, which is kind of contradictory with my hypothesis earlier, because I have a hypothesis that the 3D laser scanning would be more accurate, but it's not. Well, we are going to uncover that after this. But moving on to the next parameter, the second one is about time. The time required for the conventional method is actually only 2 hours per acquisition and 2 hours on the data processing. Meanwhile, photogrammetry needs a lot faster time required for the data acquisition, about 32 minutes. And however, the data processing requires a lot longer time, for 5 hours. And that is also the case for 3D laser scanning. Its data acquisition is actually pretty normal, but its data processing is 9 hours. It's much longer. And then for the cost for fixed cost on photogrammetry is actually quite similar to conventional method. But the cost for 3D laser scanning is a very huge investment for a company to buy the tool itself, to buy a terrestrial laser scanner. However, both operational cost on photogrammetry and 3D laser scanning is it's kind of expensive because we have to pay for the software legislation and everything. But I want to direct our focus back to the volume part, to the quality part. Why does this happen? And I took two data. I took the point cloud data of photogrammetry. I took the point cloud data of 3D laser scanning, and I overlaid them together, as we can see here in the figure. And as we can see, as we can observe also, the data of 3D laser scanning is actually popping up more often. The yellow is more often popping up. And the reason being is that 3D laser scanning analyzes more or higher ground elevation data compared to the photogrammetry. And why so? This is because in analyzing the factors, I also compared this research with a previously published research by Nguyen on 2020, where in this research, it is shockingly, my research shockingly has a higher accuracy percentage. So I analyzed this into two parts. The first one is that the project condition pollution. When I visited the project and I did the research, it is actually, the toll road is actually being scheduled for work progress, not monitoring progress. So there are cars, trucks, and people all around. And the second reason being, during the study of period, there are filtering data. So when we filter those data, we delete this data, we left a hole behind. There are no data on that specific area. So that is one reason. And the second one is the number of measurement points. The amount of data available, we know that it corresponds to the number of points that needs to be overlapped in the site. In this research, I used 5 measurement points. However, in Munyan's research, for only a 50-meter square area, they only use 2 measurement points. So that also means to a less data. So from these 2 analysis factors, we can conclude that if the project has less point cloud data, and there are a lot of factors contributing to that, such as the project condition pollution and number of measurement points, they will result to a higher chance of it being inaccurate. So to close this presentation, I want to answer the focus of the problem and objectives of this study. It can be concluded that in analyzing parameters, I analyzed 3 main parameters. The first one is the volumetric parameters and deviation values. Second one being data acquisition and data processing time. Third one being the fixed cost and operational cost. Now, from this 3 categories, it can be concluded that the photogrammetric monitor method is the most effective method in the case study of this research. And in future research, I have also a couple of suggestions. The first one is to ensure the pollution aspect of the construction is at a minimum. So, and then the second one is to add more comparison aspects to analyze the digitization optimization aspect. And these are the bibliography that I use. And I thank you all for bearing with my full explanation. Good evening, everyone.
Thanks, Abim. I think the best thing is hold your questions until the end of both presentations. So we'll get straight on to allowing Achmad to come and give his main presentation tonight.
Can you hear?
Yeah.
Good evening, everyone. Very good presentation, Abim. Thanks very much. In my current project, I use drone photography as well, and it's really, really helpful actually. And what the research that you are doing will be very promising in the future because on station you only measure point by point. With photography, you can measure continuously for the whole surface area, and that's something that we should emphasize more. Yeah? So well done for that one. Thanks. All right. Okay. All right. Thanks very much for the opportunity, Phil and the ICE team. In this opportunity, I would like to share some bit of my knowledge and experience in offshore fixed platform construction. It is quite common to have engineer present the design aspect of the offshore platform, but I think it is less common for an engineer to discuss the construction aspect of the offshore fixed platform construction. I think it is a conception that we need to be correct. Because why? Because engineer involvement extends since before construction and even after construction, during operation or even until decommissioning. So in this presentation, hopefully I can share a little bit how us as engineer can contribute the objective of successful construction, which is safety, good quality, and also completed in time and in budget. Yeah. So this photograph is actually a Bravo flow station, a courtesy from my friend from Pertamina. It reflects one example of a fixed offshore platform that we have in Indonesia. So I thank you for sharing this photograph. All right. Yes, a little bit about myself. My name is Achmad Makmur. You can call me Ahmad. I graduated from ITB in 2010, majoring civil engineering. I achieved ICE incorporated engineer in early 2017 and now en route for a chartered engineer, hopefully. My current role, I've been in various roles in the project actually, but my current role is a marine civil engineer for Tangguh Expansion Project, FEED and EPC stage. I started my career as a site engineer for building 4 ESCOP tugboat for Tangguh LNG plant, as you can see to the edge there. And then I moved on the FEED stage for the JT2 design. And then I moved as a offshore engineer for Tangguh Expansion Offshore, both FEED and EPCI stage, in which I also had assignment for landline FPSO or 204 FPSO, some little bit involvement in the Claridge platform fabrication in South of Korea. So to begin the presentation with, I would like to discuss about the overall principle of oil and gas supply chain and why the fixed offshore platform is one of the important nodes. We can see here from Wikipedia, this is the overall oil and gas supply chain. You can see further to the left, this is the source of the oil and gas. It could come from land directly, it could come from offshore platform, or it could come also from tanker, which is supplied from overseas or other region. And then it moved to the onshore side, being processed in the refinery, and then being divided into several use, like directly for manufacturing purpose, like producing chemicals, something like that. Or it can also be directly converted into heating oil or even gasoline. So that's a typical supply chain that we have for oil and gas product. Today's presentation will be discussing on this particular aspect, which is the offshore platform, not only drilling, but also on the production, which play maybe some of the most important role in the oil and gas supply, because it enables access from oil reservoir that previously only available from onshore, but now is available from offshore. There are several types of offshore platform, actually, not only fixed platform. This is a very wonderful illustration of the type of facility. The first one is the fixed offshore platform, the conventional one that we normally hear. So the intention to have this design is to have a design where the platform can be fixed and can resist all of the environmental load like wave, current, or wind, something like that. But if we move to have a deeper offshore location, the type of platform can change to compliant tower. It visually looks like similar with the fixed platform, but the difference is the compliant tower allows some compromise with the environmental load. So it allows the platform to move a little bit so that not all of the full wave loading or current loading are absorbed by the structure. So it is actually quite a clever design to have rather a bit of fixed platform, but not having an overly significant structural size. If we move further deeper, there's other type of platform called tension-like platform. It is basically a fixed platform, but is secured by tension mooring line. The second two picture here. And if we move also offshore, also called spar platform, is also quite similar with tension-like platform, but the mooring is not tension, is more like catenary. And it behaves quite stable because it has a very long cylinder supporting the platform toward the deep water. And at the end of the spectrum is, of course, the ship-based offshore platform, which is always used for the even deeper water platform, water depth, and a more complex structural arrangement. The construction of this facility are different, of course, especially between the fixed and the floating. But there are some element of those construction that are quite similar, some like modularization and offshore installation, which I will discuss. But our tonight's focus will be on the fixed offshore platform, which will be quite interesting as an entry to the discussion. As an example, this is some example of offshore fixed platform. The first one is the Bravo Float Station from Pertamina Hulu Energy, offshore Northwest Java. It is from Indonesia. We can see several platforms connected by bridge. And this is quite also interesting. This is a Troll A platform. It's a fixed platform, but it's made by concrete, actually. There are a lot of decisions behind why the concrete is made. One of them is related to the supply of the quarry in the area. But this is, I think this is the tallest fixed offshore platform outside of steel structure that we have in operating in Norway. The other example is Claridge. It is located in Scotland. It's a twin, not twin. It's a two platform connected by bridge with two jackets. If we try to understand the scale, you can see here. I think you're all familiar with Monas Monument Nasional. It's about 132 meters. And this platform is taller than that. And you can imagine that this drilling platform is 30,000 tons in weight. So you can imagine Monash with 30,000 tons in weight. So it's obviously significant feat of engineering, right? So we should be proud of that actually. So this is typical arrangement of offshore platform. Regardless what type or shape of fixed offshore platform, it's generally look like this. It has a topside component which provides support for equipment and operation, and also any life load like fluid or deeper moving or helicopter, for example. And there's a jacket component, and one might see that the jacket looks like very sturdy and supporting the whole platform, but in fact it doesn't. The jacket is designed actually to provide lateral support for the piles, and the piles itself are the one who support the vertical load. So the jacket provides lateral support for piles and conductor. Conductor is where the oil pipe connected to the underground. But it does support some small accessories like barge bumper, boat landing, nodes, and pipeline riser. And then we have a piles here. The piles here is actually primarily supporting the overall load. Even the jacket and also topside are supported and directly transferred to the ground. In some offshore fixed platform, they have like additional wing type piles, which we call skirt pile, just to increase the platform capacity, load bearing capacity. So to understand how a fixed offshore platform is being constructed, I would like to start the discussion about how an actual building is constructed onshore. First of all, if we look to this picture from the top left, they started from the piling, for example, and making foundation, and then starting the first floor, second floor, and until top up, and then completed accessory. So what happens if you have a deep sea? Are you going to adopt the same principle? Well, as engineer, we always say, yes, we can, but it's extremely unpractical. That's another word for impossible, right? But to make things worse, what about building this facility in North Sea where the wave will be very severe, very high? Yeah? So that's why people in the past who develop a fixed offshore platform, they come up with a clever solution actually, not to construct directly, but to assemble things offshore. The way they assemble it is that they create three main components. The first one, the jacket. The second one, the topside. And the third one, the piles. I'm not showing the piles here, but the piles is included. So what they are doing is that they transfer all of those components by using a barge, and then place it in the intended location, of course, during a low wave window or during very low tide and low current. And they put the jacket to be set down on the seafloor, and then they pile to secure the jacket and secure the location. And then they conducted more lifting, generally on the topside part, and including some of the accessory like boat landing, stairs, something like that also included. They continue doing so until they got the final shape of the platform, which they can do the integration, hookup, commissioning, startup, and eventually operation. So in all of fixed offshore platform, the procedure is generally like this. So it's like an offshore installation with onshore fabrication or onshore construction, some people say so. So what I'm going to discuss about our involvement here, since this is a very large topic, I will be focusing on the onshore fabrication. As I mentioned before, the approach in building an offshore structure like that actually is not only applicable for oil and gas facility offshore, but it can also be applicable for other type of facility. The first one, the onshore LNG plant in Gorgon, Australia, they have been built based on the same principle of using modular construction. So they construct all of the modules off-site, and they carry it to the final site, and they install it one by one, like a Lego. Offshore wind, of course, another example of a renewable front. They also adopt the same installation principle. And I recently realized, based on this presentation, that in Norway, offshore fish farms are also made based on the same principle with the offshore platform. So all of the engineers do not afraid that if oil and gas somehow is ended, there are still very important usage of this approach. It still always be required by the world. And that's one of the examples how we can support the world growth. Yeah. Again, for onshore modularization, actually, it really helps in minimizing environmental footprint. I remember when I was in Korea, when they fabricate these Gorgon modules, they need to they need to wrap the platform and to make sure there are no insect or there are no rodent that is included in the module that being transferred to Australia. So it's very strict process, and it's very, very. I feel very proud as an engineer that we can do that. Right. So on the jacket construction, this is an example. Yeah, we're not talking about small structure only, but we're talking about big structure. This is the largest steel jacket ever constructed and installed. You can see the scale between the ship jacket and also the oil tank there. This is a bullwinkle platform, 416 meter tall, 44 ton, about 3,000 plus member and 1,000 plus joints. So we are talking not only small structure, but also big one. But even this large structure, they are being constructed based on this simple principle, actually. First of all, we procure the material in terms of plate or in terms of cylindrical member. And then we cut some of them to make a note or sub-assemblies. Like you're making Lego, you have different pieces of Lego shape, right? So you make that one by one. And then you assemble that into a block assembly. And then you coat it, some of it, so to reduce any coating done on the outside of the shop. And then you assemble it together into a sub-assembly, which is larger here. And the sub-assembly often involve a rollout and appending process, which I will share further after this slide. And then after that, they complete it by doing full assembly, where they complete the whole section of the jacket, weld everything, and doing a touch-up. And also install some of the additional appurtenance. Appurtenance is like an accessory that is required, like a J-tube, conductor, or boat landing, or anodes, so something like that need to be. And it is also important that they perform weighing to make sure that the final product is still within the barge capacity, because weight is very important for offshore facility. Because during the transportation and during the lifting and even during the operation, the weight should still be within the design assumption. And then evidently the jacket, the finished jacket is loaded out for offshore installation. So the next about the jacket is I would like to highlight some of the important things on the jacket construction. The first important thing that comes to my mind is the nodes. The nodes is the joint between tubular of the jacket. Why it is important? Because it is actually a point where multiple members connected into one single point, and all type of loading are directed to that point. So it is very important that this node perform very well, because if not, it is no use to have a lot of members if the nodes are failing, because it can create single point of failure. It is individually built from a hollow section to meet design requirement on the node geometry. And the shape can be very complex. Some of them can overlap each other, and the weld can also overlap each other. And some of them are provided with local strengthening, like increase of thickness or maybe additional stiffener in the inside. It's quite complex. And it is designed to resist conventional and concentrated loading, in addition to fatigue loading, which is very important for offshore structure. Because of this criticality, almost all of the offshore fixed platform codes provide a very strict guideline in how to fabricate this type of components. The example is this guideline from API. So in API, for one type of node, they provide a lot of guidelines. For example, the angle of these nodes, the location of any welds, the thickness of incoming member, the slope between larger member to the smaller member. So those are really regulated. And why? Because we want to ensure that the node can adopt the equation provided in the code. And why we need to follow the equation from the code? Because they have provided a very good experiment and research in the past that allow such kind of node to have a good predictability in addressing a load. So we will not have any surprise if somehow the node is loaded within the design requirement. So this is one of the example for us as an engineer at site. If if the fabrication of the node involve a complex structure like this, engineer involvement is very required to do a verification on where and what type of joint and how they perform the installation actually. The other one, also related with the node, is regarding this picture. Can anyone guess what this picture is about? So this is actually where the welder joined the welding. So they provide some kind of covering like this to ensure that there are no excessive wind coming to the welding area, because excessive wind will carry oxygen or any other air contaminant that actually would reduce the weld quality. And it is important to ensure that the weld can be made almost perfect, because the weld is one of the important components that transport the load. Yeah. And this is one of the gentlemen who doing the welding. And I always put high respect to the welder, because it is very close to an art. Not many people can do it very well. And they are at the forefront in creating a very good structural node, especially. So why in offshore structure, especially jacket, the welding is excessively used? The first reason, of course, is cost and schedule. But what actually behind that cost and schedule? The first one is weld joint in API is very well prescribed. So all of the international code allow a very good guideline on making a very good weld joint. And also, we can see that the node shape can be very complex. And by having welding, actually, we have a greater freedom in doing the design. And then the weld allow for area and more robust joint connection. And also, if we use bolting, for example, we need to use gusset plate to connect between bolts, or we need to use flange to connect between tubular. And that's not very efficient in designing an offshore facility that's subjected to current and wave flow. So that's why by having a welding, we can have a full tubular and smooth, good aerodynamic structure. And also for out of tolerance, it can also be better adjusted. We have called like buttering procedure. If there's a joint gap that's quite high, you can just like build additional weld section to connect those gaps. And the corrosion resistance is also better, because you can coat the welding with the same coating like the structural member. And it has a better thorough joint quality test method, because you can practically see through the full section of the weld by ultrasonic, radiography, or any other inspection method available. There are several types of welding, especially, and these are selected based on the productivity, based on the criticality of joint, and sometimes based on the accessibility. If the joint is not accessible by automatic method, they use a stick welding, something like that. So it's really depending on the construction team, but some element of engineering is also involved, especially for critical weld location in the joint routes. Okay. The next aspect that I'm going to discuss is regarding on the joint jacket assembly or roll up. So I would like you to look in this picture first. This is the final picture when the jacket is completed. But actually, before it's completed, the shape is like that. You can see it looks like something like a bread, like connected together and becoming like this. Why is that happening? Because first, they want to do a lot of welding as much as possible on the ground. So they only do the rest of the welding above ground with as minimum as possible. The first reason is safety, of course, because if you are doing activity above ground, you can be susceptible to fall risk, fall hazard. The second one is also productivity, because you don't want to carry the welding rod and equipment using stair or ladder or crane. If you put it on the ground, it will be very, very fast. And also, you want to have a structure that's robust from the wind, even during fabrication. So that's why they put it in the lay-down position. Once they have weld enough joint for the side segment, they roll it up, something like this in the second picture. They connect it and they did tuck weld until it is secure, and then they complete each weld one by one. So actually, this is a clever process to minimize risk and also to obtain a lot of opportunity in designing a jacket. And you can see that a lot of cranes are working together to assemble the structure. This involves a complex lifting, and that's where the structural engineer need to contribute to ensure that the lifting and roll up can be done properly. This is also another example, and this is an example where the roll up is not only on a section but the whole jacket. We call this appending. So creativity is the limit, actually. Creativity and equipment and the structural analysis. So depending on which method is better, which method is more productive, so that's where you select how you're going to uplift or append the structure. One important thing with regard to the lifting, and is applicable to transportation as well, is that we as an engineer at site, we always want to have a structurally determinate lift. Why? Because if you look at the figure on the left, we have a 4 sling connected to 1 hook. Figure on the right is 3 sling connected to 1 hook. The left one is what we call statically indeterminate. What is statically indeterminate? I think during our old campus life, we understand that the calculation of load distribution between each sling would depend on the stiffness of the lifted structure as well. If the stiffness happen to change a little bit, the load distribution will also happen might be quite significantly. The reason why we want to have a statically determinate is that in the fabrication situation, the center of gravity of the load can always shift because it cannot be 100% predictable without weighting. And then the type of the sling can also be slightly changed. Like, for example, one sling could be longer, one sling could be stiffer, like old sling and new sling. And if there's a change in the sling stiffness in the indeterminate lift, the load distribution between each sling will be could be significantly different. And that's where we have a sling failure, because maybe some sling are loaded heavier compared with the other sling. But in the statically determinate lift, if the sling stiffness is changed slightly, if the center of gravity is changed slightly, the load increase in one of the sling will not be that significant. So that's why we always aim to have a 3-part sling arrangement. It is important because we need to check structural, lifting point, rigging equipment, also crane. And also there are several types of load factor that need to be considered in the design. If we can have the 3-part sling arrangement, the load factor to be considered can be much more simpler. The next aspect is on the topside structure construction. As mentioned before, the topside is provided to provide support for operation equipment and also for live loads. It is not subjected to wave and current fatigue load, just like a jacket in a fixed offshore platform. But it might be subjected to vibrating equipment load because the topside is designed to carry a lot of rotating equipment like pump or even a turbine generator, something like that. And it consists of other type member other than tubular, not only tubular, it can also prismatic member, which is governed by AIC code. I think that one of the major difference between jacket is that the topside is prone to clash or design mismatch because there are a lot of multidisciplinary interface involved in the design and fabrication of the topside. And that's why they have more complex structural configuration than jacket. And since a lot of equipment cables are located, the construction working space are generally quite very small, very narrow, and this is where the mistake would happen. And they can also be designed as a modules, so that's why the governing load, not necessarily the operational load, but can also lifting load. Yeah? So this is a challenge. The Claridge quarter and utility topside weight was almost 18,000 tons. Right, so this is the typical aspect in a topside construction sequence. The first one is the same. We have a material procurement and cutting to make it into a small segment. And we then continue with sub-assembly because in topside, they also have nodes, especially the connection between the jacket to the topside. Sometimes they are made in tubular section. And then they constructed into block, which is a small Lego section. And then constructed into pallet, larger Lego section, and then coated. And then that's where when there's a major equipment, the major equipment are then installed before the topside completion of one modules. And then after that, it is completed into full assembly. and equipment full installation like cables, sensors, handrail, rating, something like that. And then it will go for the onshore equipment commissioning. And then again, it follow the waiting process and until it is being loaded out for offshore installation. The overall construction sequence is quite similar actually with the jacket, so I will not discuss that further. But I would like to discuss since the topside is very prone to class and design, design discrepancy between multidiscipline. So I would like to share you how actually we try to ensure that the design is conforming since between the design drawing and then also the fabricated structure. The first one, this is the overall hierarchy on how the design is progressing. The first one starting from the design basis and also the codes, and then we translate that into project specification, and then we translate that into a design report, and then we visualize that into a design drawing, and then we change that into shop drawing to make a small section of the structural member drawing, and then once the structure will be fabricated completed, we document that as an as-built drawing. So during this process, there are inevitably design change being done at site. So the way we manage that normally through several processes like site queries. So this is something where the site team asks to the design team office why this something different, why this information is not provided, and why there's a class. Also, there's a record called field design change, where there's a quite major design change being done at site, but not yet captured in the shop or design drawing. And then there's also a red line markup, which normally happen for small change like cutting some member or relocating some member that is not structurally significant. And sometimes if those are not captured in these three process, there are also several quality process that is required to capture this, like punch and defect list, observation report, or in the highest form, we can record that into quality non-conformance report. This is actually some example of clash that possibly happened during construction. If you look to this photograph, you can see there's a beam connected to the penetration. And supposedly the bottom of the beam flange need to be fully connected to the web of the larger beam. But since there's a penetration here, so they need to snip the bottom flange to prevent any clash. So this is where the engineers need to come to understand and to decide whether this deviation from their standard drawing is acceptable or not. Of course, if you look here, it looks very acceptable, but in some area, it could be a design change that is not acceptable from structural point of view. The bottom example shows the misalignment. It's not very clear here, but between the beam connection and also the incoming beam, there's a bit misaligned. It is often that the misalignment is very difficult to rectify. So engineers need to come up with a good design solution to justify whether this misalignment can be captured for operation stage. Another point here, they have some damage in one section of the beam, but they are unable to procure another one. So instead of replacing the whole beam, they just need to cut and propose to leave the remaining of the beam. There's obviously a big question about this unstaggered connection because it's very one-sided flat, but this sort of problem that engineers can also face. And as engineers, we are also human. We are also prone to mistake. We can also come with incorrect drawing that is passed from engineer quality control. So we need to acknowledge that it happens, and it somehow is already being fabricated. We also normally require to justify or try to do some further calculation whether the correct drawing can still be used. This is another example actually where the beam are supported by horizontal bracing. As we know that horizontal bracing is not supposed to carry vertical load, but somehow it happened and is in line with the drawing. So once we do a sidewalk and we see this situation, we obviously need to understand if the bracing going to handle the vertical load very well. So I remember at the time they did a finite element analysis or more structural analysis to now consider both horizontal stiffening load with the vertical load from the beam to make sure whether the result is acceptable or not. All right, so many of you are novice. Yeah, it happened. Unfortunately, I have not seen a mistake this wrong, but I Googled, it happened. I've seen something close to this, but again, as engineer, we cannot always assume that people know very well about how the structural behave. So that's why actually it's always good to have another pair of engineer eye on site, do a site walk just to help our construction team and quality team in making sure that the facility are built. This is very typical problem, this type of class, because some small piping or small equipment, they are not fully modeled in the BIM, in the building information management 3D model. So that's why it's quite often that these classes happen. And this is where the engineers, multidiscipline, need to be creative in handling these issues. All right, the next part is about the typical interface that the civil and structural engineer will interact during offshore fixed platform construction. The first one is quality team. I always see quality team is our best friend, because they are the real people who validate, who check between the drawing and the actual fabricated structure. And through their experience, years of experience, they often know better, or they often have a better eye in looking which one does not correct based on the standard drawing. So quality team is actually very important, and it's very good friend. So I always, an experienced quality team, actually, I always consult them to have their additional input in addition to engineering feedback. The next one is, of course, the construction team. They are the one who make this realize, who make the big structure realize. They make it happen, and they ensure that the method, the sequence, and also the timing are met within the target. And we work with them closely. For engineer who work in the fabrication yard, we work closely in making method analysis or a shop drawing or something like that. For the one working client like myself, we work with them to make sure that the method, the sequence can still meet the design intent. Health, safety, and environment is also very important, because as engineer, we also often interact with them in many occasions, like how to improve the temporary facility, or how to improve the lifting, and how to improve the personnel location is very important. Also, how to place the waste or environmental chemical hazardous material, how to select material that is less hazardous for the environment. Of course, other discipline engineers like piping, electrical, and so on, mechanical as well. So it's a lot of discipline engineers need to be consulted. The vendors, sometimes we also discuss with the vendors on how the vendor can support the project better. And in some aspect, marine surveyor, marine warranty surveyor, or independent verification body. So this is the third party that are involved to help us to verify that the design are still are within the industry requirement. All right, so this is my last slide. How we can contribute to health, safety, and environment better as a structural engineer or civil engineer. The first one, our primary role is, of course, to deliver a design, whether this is design analysis, method statement, or any other document. So that's our primary cause. So we need to excel in that area to make sure that we deliver it in excellence. What means in excellence is that we deliver it safely, and we deliver it in the matter of very efficient for our construction team to allow to build it properly. The next one is that we need to also continue to participate in the HAC program. Some of the program that I'm involved with, like the toolbox talk in the morning, like this photograph, it's very useful to meet with the people on the floor. Safety observation card. It is like when you notice some good safety behavior, you can comment that, record that, and some can be turned into a token or a prize. But if you see any safety improvement required, you can also record that and communicate it with all of the relevant personnel to improve the safety condition. There's also called the HAC self-verification program. This is like a more detailed version of the safety observation card. And also safety awards, where we award personnel, we inspire people to do better on safety. Also, as an engineer, I always encourage the engineer to do a structural work at yard. again, we rely on quality and construction and all other colleagues to help to build, to realize the design. But our eyes at site actually is very helpful because we can give another perspective that maybe is not available in the current construction yard. And then I always want to encourage our fellow engineers to care for others because construction yard is a very dangerous location, very dangerous place. A lot of things can go wrong and people can hurt because of accident. So talk with fitters, for example, welders, scaffolder, lifting team, all people in the yard practically, just to make sure that you can build a good connection with them, because they can also be a very good source of information if something happens, something wrong happens. For example, if there's any structural damage, structural defect that not being actioned properly, we can always get that information from people on the floor. And the last one that I think is very important as engineer, at least from my point of view, it is very important to be courageous to speak up against principal design deviation, because sometimes schedule or cost driven driver can influence how we decide regarding the safety of the design. So this is where the engineers need to be able to speak up and highlight any wrong in this kind of deviation, to make sure that we have a facility that will operate safely, can be constructed safely, and become a pride of us, both the engineer and all people involved. Right. This is one of example that I took from Saipem Indonesia Karimun Yard. This is a very good actually safety conversation between the workers and the safety team in a very comfortable environment to allow them raise their concern and to allow them learn about the improvement in the safety process. So that's conclude my presentation. Thanks very much. I'll be happy for any discussion.
Thank you very much, Achmad and Abin. That's two really good presentations there. Thank you very much for putting the effort in to do that. Now questions. The best thing is, first of all, are there any questions from the room? Ask obviously verbally, and then I'll have a look in the chat as well. So anything from the room, first of all? Mike?
Yeah, I suppose you've got to come to the microphone. No, actually, a little question for each speaker, if I may. I'm interested to know, because of the amount of data that must be being processed for these procedures, I assume you have to have very huge computing power, and that it must work very well. I mean, is that correct? Correct.
I use the computer on iOS.
Unfortunately, I don't think everyone can hear your response.
All right. Thank you for the question, Mr. Mike. I actually use Utama Karya's computer. I forgot the detail on each specifications, but I do remember their own graphics card is as well as expensive as an Avanza. Yeah, I remember that part only. But it's it is a supercomputer. Yes. But I forgot the specifications. So yeah.
Oh wow.
Yeah.
That's a very good answer. Straight in your advance. Okay, and then I've got also a fantastic presentation. I mean, some of the numbers are and some of the facts you tell us there are amazing. I'm curious. I mean, obviously, the way you show that, the importance of welding becomes huge, because it depends so much on the quality of welding. I mean, you mentioned the importance of this, and in fact, how welding is such a skill. I mean, not many people do it well. I'm just wondering about the control of the welding, and also whether or not there is any further heat treatment or something like that. I mean, these are such huge welded, joints. To actually put them into something to heat treat them, which I know you can do for smaller scale welded sort of joints and connections. But is anything done after the welding has been completed to either improve it, make it better, or what? I'm not sure. It's just it seemed like a really important but a fascinating issue.
Yes, I think you pointed very clear and very right, because welding plays a very important role in the jacket fabrication. I'm stepping outside of my discipline here, because actually welding is governed by welding engineer and also quality team focusing on welding. But my understanding is there are several elements to come up with a good welding. The first one is the welder itself. They need to be certified, trained, and also qualified to do the job. So they do some kind of like a welding qualification, where the welding is assessed, the welder is assessed with regard to the ability to prepare the welding. And then their skill is also judged based on the position of the welding. Some weld can do the welding in horizontal position, but if they move to a more advanced level, they need to be tested doing in the vertical position or even diagonal position. And that's the process that is heavily regulated by the American Welding Society code. So the complete process is very nature. So in terms of the welder itself, they are trained, they are tested, and then they need to be qualified. And then the second one is the welding product itself will need to come for the quality inspection process. Some of the welding, they need to be 100% tested to know that how many defects are available. And if there's a defect is categorized in percentage of how many percentage of the defect in one rank. If the percentage of defect of the welder is very high, the welder will need to be reflected from the floor and retrained again until it can achieve the level of defect rate that can meet the project requirement. It is also gathered by the process. Yes, so it's very important to have that process of it. And also the quality control report, the welding result, the type of the welding, the inspection result, all are recorded and need to be traceable even until the project is completed. So it's very extensive process. And the second one, with regard to the treatment sample method, yes, but it happened for some members with a very thickness. That a very thick member, they require some post-heat treatment or even trigger treatment. It's really depending on the welding parameters. I'm not at the liberty to discuss in detail, but my understanding is yes, depending on the complexity of the joint and etc.
No, it's not very good. Thank you very much.
Yeah, thank you. I've got any other questions from the floor? David. Yeah.
I work for a company that offers water supply treatment works, and we have 3D clash analysis programs. And we didn't. I mean, obviously there is still so many pipes and facilities going here, there, and everywhere, particularly in the operating platforms. I just wondered if you could say a word or two about 3D design. Surely you do some sort of 3D design, which would help with the clash analysis. I mean, I thought you tried to pack too much into 10 minutes, and you had a lot of detail up there that we just couldn't possibly read in the time. And I think you can take a lot from the second presentation by keeping it simple, and a lot of information could be provided by pictures rather than words. And if you have tables, it's often best to present as a graph. So I think you probably learned a lot from the second presentation. So I hope you don't mind a little bit of criticism. Okay, so first of all, about 3D analysis.
Thanks, Mark. Yes. Yes, 3D model, what we call the 3D model, or people also call BIM, building information management system. It's very essential, and now it's getting more accessible. But the challenge in implementing that is that not all facility can be modeled 100% because of the resources required, and also the uncertainty, the inherent uncertainty in regard to the construction method or construction status. For example, we do a 3D model during almost end of the detail design, but some vendor can always update their equipment, the orientation of the piping, small piping, Some vendor can have maybe a different or wrong in the model, 3D model, or also maybe some site adjustment is required. For example, to move some of the column a little bit, something like that. And that's not always being captured because of the resources constraint. And then in the oil and gas industry, as I understand, some small piping or cables, they are not modeled in the 3D model because they are site plan. I mean, they are not planned in the drawing. But once they have done inside, the team decided which road is more efficient, and they just prepare that road. And sometimes that is not modeled in the 3D model. So when the first team lay the cable, for example, the second team lay the pipe, the clash could always happen. So that's very important point if there's any way to ensure the consistency of the model even until the end of the project. But at the moment, I think it depends on the resources and it depends on the willingness of the project to which level the 3D model will be incorporated.
Okay, thanks. Anything else? Any others from the room? I'll just jump to the question on the screen, and it's really about scheduling and design loads. So over to you again, Achmad, I think.
Yes, this is from Chandra Yuki Kusuma. He's actually my classmate in the college. He's very clever guy. So very, very tough question as well. So thanks very much, Chandra. The first question, I don't think I'm the full competent person to answer this because there's a lot of factors in making sure that we achieve the tight schedule. But from engineering point of view, that's something that I can share. I think it is important for engineer to come up with an efficient design that can be constructed safely and also can be constructed more efficiently. For example, like the roll-up process in jacket, that's part of a design innovation that the engineer can also work with construction to make sure that roll-up can be done. So that obviously really increase the efficiency and safety of the construction of the jacket. So I think from engineering point of view is that making sure that from the front end, we come up with a design that very efficient and also with the material that are accessible in the region, and also allow some flexibility if there's some requirement at site to be adjusted, something like that. So maybe not answering fully, Chandra, but that's a bit from my point of view. The second one, what is the advantage in Indonesian sea for design and fabrication? All right, that's very good. Also good question. Of course, when compared with the North Sea, Indonesia have relatively benign water, low wave height, and also current quite small. Some of them is very strong in Tangguh, but some of them are very small. Obviously, we can have a more efficient jacket type if we assume the design with the lower environmental load. And also the other one is regarding the installation window, because in the North Sea, they try to find the window, the months where the tide or the storm is not happening. So when the water is the most benign compared in other periods of the year. I think in Indonesia, we generally have quite a similar trend, although we have rainy season, something like that. But since we do not have a very big variation in the wave and also environment ocean condition, we have a larger installation window that can be utilized in construction platform. Maybe that's a little bit from. Thank you, Chandra.
Thank you. I might have another one. I can't see any other questions on the screen. I just had one question myself to try to bring the two talks together. Abim, when I looked at the size of those structures, and I was thinking as an engineer, how do I go and inspect and make sure that this thing has been built correctly? Is there any of your techniques, remote sensing methods that can be employed, obviously hand in hand with BIM, to solve that problem?
Well, okay, thank you for the question. I think my research can be implemented in Achmad's research as well by analyzing all the quality of the works, such as like the flashing. But in reality, it's actually pretty hard to implement those type of photogrammetry and 3D scanning, considering the tool itself and bringing them to offshores. But yeah, it is possible. It is possible to implement the method so that we decrease the amount of manual work, and then hence also decreasing the amount of the what do you call it, the clashing that happened in the offshore. Yes.
Okay, thank you. I can't see anything else on the screen. Final call. Any further questions before we get on with having our dinner? If nothing else, thank you once again to both our speakers. They were very good, very interesting. And thank you both for making the effort to come and talk to us. I really appreciate that. Nice turnout tonight. Thank you guys for making the effort also, and the organising committee, and to everyone online. Have a good night. Thank you.
Thank you, Phil Woodmansey, for guiding the session. Once again, thank you, Achmad Makmur, for your excellent presentation. Also, thank you for our featured speaker, Abimanyu, Satrio, Ambiarto. Ladies and gentlemen, we have now reached the end of the event. Once again, thank you for your participation. We hope to see you at the next event. At last, good evening and stay healthy, everyone.